myself as part of the group. So please join, so that way we can build a network. And this is the 9th school, so we're going to, hopefully get most of the people that have been coming through the last 9 years. And so it'll be a nice network to be part of. So if you're on there, please find us, okay?
Okay, so yeah, without further ado, please welcome Efrain Rodriguez, one of the best chemists I know.
Really? How many chemists do you know?
One of the co-founders of the school and a close collaborator, and he's given many good talks through the years. So we're interested to see what this is about.
Yeah. So when JP and Nick asked me, like, why don't you just give like a chemistry talk? I said, okay, fine. What do you want it on? So whatever you want. And I thought, okay, I'll just stitch something together. Franken talk, and then I think JP took it literally and titled it Franken Growth. So it'll be something like that. We're going to be covering several topics in material synthesis and crystal growth. But at the same time, I think you'll see that many of you who do have a physics background, that sometimes chemistry does come across as a little bit of like magic or mad scientist kind of work. And hopefully I'll try to demystify that for you today. And since we're focusing on superconductors, I want to hit on superconductivity as much as we can. Not every example will be a superconductor, but I'll try to get there whenever we get a chance. All right. So JP showed this on day 1, which is a very important report if you're interested in quantum materials, because about 10 years ago, that phrase came into existence, or prominence, and then we have sort of concrete examples of what we're after, right? But there's also another report. Actually, there was that same year that many people convened for this one. There was another one that was called synthesis science, and of course, for many chemists, organic chemists, for example, or some inorganic chemists, it is part of their training. But I think for many of us that make materials, solid state, or bulk or thin films, maybe it doesn't play as big a role, right, in our graduate training. That's one of the reasons we decided to have this school, to address some of these very challenges. And so we must be able to make the materials we envision, and there must be some kind of science of synthesis. How do we get to the compound that we're after, or the functional material that we're after? And so much less effort has been directed at predictive science as well. It is a very tough problem, and I'll tell you a little bit about why that is later. And we need to understand where the atoms go to achieve desired structure. So I'm a solid-state chemist and also a crystallographer, so many of the things that we do is X-ray neutron scattering, so that we can develop those structure property relationships. So that's kind of a strategy, of course, that we've always had, but can we do more than that? All right. I want to emphasize that chemists should be part of this community, a lot more than I think happens even to this day. We've been working hard at FQM to do this, but let me give you an example here, very clear one. Hideo Hosono, a chemist who changed the field by discovering an iron-based superconductor. How was this made? Was it on design? No, right? And if you read one of Hideo Hosono's papers, a perspective he wrote, he's working on transparent conducting oxides. He made a copper-based material, copper selenide with a rare earth oxide. Said, let me make a magnetic one. What's a nice magnetic element that you'd want to throw in? Obviously iron. And then it became superconducting, right? So my point here is that chemistry can also impact physics, and so I think it's a fun place to be in. So what I'm going to outline today is I'm going to say some things about traditional solid-state chemistry, its limits, its promise. Then I'm going to go into chemical vapor transport. I'll say something about hydrothermal thermal syntheses, chimie-douce, so it's called soft chemistry. There are ways to access compounds that you wouldn't otherwise from just conventional techniques, okay? So I'll show you some really interesting ones, including what we call the instant superconductor, just add water. Okay, conventional solid state methods. We have to work with an energy landscape to find the compounds that we're after, certain structure types, for example. And one of the things you must know is that it's a very powerful technique, even though sometimes it's derided, oh, it's just shake and bake or beat and heat, right? Sometimes people say. It's very, very effective in actually getting many of the compounds that we've already have in the database, for example, today. You can make many compounds, oxides, chalcogenides, nitrides, halides, maybe mixed anion systems as well, intermetallics, I forgot to put that on there, but obviously you can do that. So how does it work? It works by the fact that you take your reagents and you're just going to mix them as best as you can, put them into intimate contact so that you have diffusion at the interfaces of your reagents, right? And so say I'm making a ternary phase, what you're going to first get when I mix A, B, and C, if I want to make a ABC compound, let's say, I'm going to make at those interfaces first the binary compounds, okay? So there are many intermediates that form along the way when you're doing solid-state conventional syntheses. And you must be aware of that. Why? Because many times what we struggle against are impurities, right? That is the number one enemy for the solid-state chemist, is that impurity phase, because it could dominate, say, the properties, right, of what you're trying to measure. And eventually, you get further reaction because these interfaces are high energy compared to the bulk, and so they start to go away, then you start growing your product there. Now, what do you need in order to get solid-state diffusion? What parameter needs to be jacked up? This is cool, so and I lecture in this general chemistry, so I'm going to treat it like that.
Temperature.
Temperature, right? So that we can get solid-state diffusion. And so that's why we're running these reactions at 800, 900, 1000, or as Ryan Baumbach said yesterday, 1200 degrees Celsius, right? That is what we're doing when we do solid-state chemistry. That can be very useful because we can wipe out those impurity phases, right? But it'll turn out to be a limit later. Okay. You can do other things if you don't want to be limited by solid-state diffusion. You can put it in a liquid, right? And we call that a flux. That's one of the practicals that we usually do is a flux. So that means that now you have, you pick up the kinetics of mass transfer by having your reactants dissolve completely in your flux. Now, what you should be aware of is that if you say you have reagent A, you may get to your final product T that precipitates out of the flux, but you may also get an intermediate product in there. Many times you will, because your flux will react with your reactant, right, or your reagent. Okay, and sometimes that means that you may get inclusions, for example, in a single crystal if you're growing them that way. So you have to be aware of also the limitations that you may get out of flux syntheses. Okay, what are the advantages? And this is the reason I say it shouldn't be knocked down too much, is that it's easy to do, right? If you just need a few things in the lab, you need a furnace, you need a mortar and pestle, you need a pellet press, and so forth. And if you have oxides, even easier, because you can do it in air, right? You can just put them in a crucible or boat and get going. It's great, I'd say, for exploratory work, right? Because it allows you to easily do substitutions. Aliovalent and isovalent. What does aliovalent substitution entail? Because I hear the word doping a lot, and sometimes it's thrown around a lot. What is aliovalent substitution? Come on, this is a material synthesis workshop. What does aliovalent substitution mean? No? What is isovalent? If I'm substituting calcium for barium, right? Isovalent. If I'm putting in potassium for barium, right? I'm doing aliovalent substitution, and I have one electron less, so I'm doping, right? So solid-state synthesis is really great for doing these kinds of methods. recuperates, right, we get to the superconductors that way. So those are things that you should be familiar with as you read papers and look at how the materials are made. Okay, and if you're doing something beyond oxides, of course, you will need glove boxes, maybe a manifold for doing sealing or manifold for manipulating in an air-free condition. So those are some of the things. Okay. All right. Oh man, the animation didn't work on this. It was supposed to be a pop quiz and there was nothing written on here, but all right. You're gonna make me IPCO superconductor. What are the things that you should think about? All right. Think about the reagents, right? We're making an oxide, but it's not exactly, it's not going to be exactly just oxides of the constituent elements. Maybe you want to do a mixing of the two, right? So those are some of the things you can think about. How about carbonates or nitrates or hydroxides? Should I have a flux or no flux, as an example? Okay. And one of the things to remember is that those phases grow at the grains, right? Sometimes the reaction just is diffusion limited at, say, whatever temperature you're at, and you have to just remove it, regrind, restart, refire, repelletilize, and go again, right? So it requires multiple grindings and heating profiles. And again, pelletizing helps put those grains into contact with each other. If you don't do that, then it's likely that your reaction's not going to go to completion. And so there was a question yesterday to Ryan Baumbach about how fast should things grow, or how fast should... Well, I want you to think that there's also kinetics. We've been so focused on thermodynamics, but kinetics is also important, right? Diamond is not the most thermodynamically stable phase of carbon, but it's going to take forever for it to get to graphite, right? Because of kinetics. Think about it for crystal growth and material synthesis as well. Okay, think about the melting points of your reagents. My PhD advisor always told me, just go to the Taman temperature, which I was like, what's Taman temperature? It's not something you can find sometimes online. It's like about 2/3 of the melting point of your oxide in Kelvin, right? And if you go to that temperature, you're going to get good diffusion so that you're actually starting to make your product if you're making, say, an oxide. Okay? So think about melting temperatures and how you don't have to get to the melting point, right? Sometimes our furnaces are limited by how high they can go, but get at least to an appreciable diffusion temperature. And think about the atmosphere. I mean, not think, but think. And that might require extra oxygen pressure. It may require, say, ammonia or hydrogen or an inert atmosphere like argon, or it may require vacuum. Okay, so think about reagents, temperature, time, atmosphere before you start getting on your synthesis. All right. Okay, great. And this one's... So what do I do first? How many of you know how to make IPCO? How many of you made it? Many times. All right. You don't count, you're instructors. All right. Any student? All right. What are some of the reagents you used? So many times people use the oxides, right? Yttria, barium, a lot of times we use the carbonate forms of those. Rare earths, we tend to use the oxides. They do take up water or CO2 from air if you just leave them out. You know, there was this discussion yesterday about your reagents. Check your reagents. They may not be what Sigma Aldrich tells you it is. They do age. And so what does that do? It leads to error when you're at the balance, right? Because you're not measuring barium oxide, you're measuring a combination of carbonate and hydroxide. So just go to the carbonate, let's say, and then you can be sure that you're being as precise as possible on it. Yeah, Keenan.
I was going to make lanthanum nickel oxide, lanthanum oxide, nickel oxide, and irresponsible use of hot nitric acid, but I'll spare this.
Hot nitric acid. Yeah, I would have think about, you know, the greenest way to make compounds as well, so that you don't have too much waste. What about copper though? What kind of copper would I want? Yeah. Which one? CuO, right? I want copper too, because that's the oxidation state I want, right? So these are common starting reagents. Dry them, right? Make sure that they are what they are. Grind and mortar and pestle. Do it really, really well. Put some elbow grease into it. Press into a pellet. Heat at 950 in a pure oxygen atmosphere. Regrind, refire, and then hold at 500. And then cool down to room temperature. This is a common recipe. Yes?
So regarding CuO, or having the right oxidation state,
how do you know?
Is there an easy way to understand, like, why is it much easier to think about CuO and then the diffusion of copper in the same oxidation state to react with another reagent to give you what you want, rather than CuO2 or something else?
I think in this case, it's all about just starting out at the right oxidation state, so that you don't have to do any what we call redox chemistry, right? We don't have to do reduction oxidation. Your barium's always going to be 2+, yttrium is always going to be 3+. The one that's variable with all transition metals is going to be the transition metal. So if you don't have to do that redox chemistry, now it turns out you kind of will in this compound, of course, because it loses oxygen like crazy. And that's true for many metal oxides. Any metal oxide will be in equilibrium with the surrounding air, okay? And as you heat up, it will outgas more oxygen, right? And so in some oxides, it's much easier than others, and this one is particularly easy to outgas, right? So cool down where the partial pressure of oxygen can be held higher with respect to the oxide, keep it running there for several hours. I think this one's like a day, and then you cool down. So
do I think about it as like CuO, the copper, is diffusing from that bond right to where it wants to go in the...
Yeah, because...
rather than going through an intermediate reaction?
No, so what happens when you go to high temperatures is you have to break those bonds in that solid for that particular crystal structure type, and it's going to get to a lower energy state by forming new bonds at a different crystal structure type. So that has to happen, otherwise that phase, whatever you're after, is not going to be thermodynamically stable, right? So that, yeah, for sure, that has to happen. That's the way I would think about it, yes. Just so you remember, these carbonates and hydroxides, maybe nitrates, I don't know, Keenan, maybe you do nitrates, they will all outgas, right? So you're not going to do this in a closed system, otherwise your ampules are going to explode, and of course we've all had ampules explode, but you try to minimize how much you do damage to your furnaces, so your PI doesn't have to pay so much. But anyway, so if you then do the stoichiometric ratio of the metals, you'll see that we're not quite at 7, and that's why we're always having to do this in excess oxygen. Otherwise, you'll be left with the green superconductor, right? The one that's oxygen deficient in there. So that's just an example. So what are some of the drawbacks of solid state synthesis? I already said, you have to go to really high temperatures. Your diffusion limited sometimes. And so one of the things is that we can't access many times those metastable states, right? Because when you're at such a high temperature, you're going to get to the global minimum of the free energy of that particular composition space, okay? So there are many people nowadays trying to think about how to make metastable inorganic solids with extended structures. This is a nice article by Dave Johnson. And the number of inorganic compounds is dramatically less than predicted. What we know today is dramatically less. I'll show you by the numbers later. And so knowing how to get to a design structure is the holy grail of solid state synthesis. And this is by Kristen Pearson out at Berkeley, talking about predictive synthesis of inorganic materials remains a grand challenge. And I hope that the funding agencies also agree that this remains a grand challenge, because I think there are many interesting compounds and materials to make. Now, of course, in the age of AI, they've sort of started to get involved in all this as well. There was the famous article from Google, GNOME as it's called, that predicted 2 million new materials. right? This was in 2023. But actually, we already knew that. As I said, this review article by Dave Johnson, he plots in decades here the number of compounds that are possible just from combination of the elements, okay? And then in orange is how many we've actually have found. So these are just the elements. These are binaries. These are ternaries. These are quaternaries. We're so far off in magnitude, right, where we could be just based on the simple combination. So you don't have to have anything quite this fancy to predict how many can be out there, right? You can already just see that from the combination of the elements. So why is that? Again, because we're limited by this conventional solid state techniques, okay? So there are ways to access what I would say are local minima in this complex energy landscape, as also said, written by Martin Janssen, about how to get higher up on these here, okay? So it will require, obviously, some exploratory work. Sometimes that seems like a dirty word, exploratory, but actually I think it's really necessary in order to discover new materials. Okay, let me talk about some of the techniques beyond, right, the conventional solid state. You're doing one of the practicals in my lab in chemical vapor transport, so let's go through a little bit of that. All right, CVT is sort of becoming very ubiquitous now because of the fact that a lot of people are interested in van der Waals materials, and so are we. We work mostly in the space of chalcogenides, so I'll show you some TMDs, chalcophosphates, and maybe, and of course, the iron-based superconductors, selenides and sulfides. These are all, if you want to see some articles of VW materials, these are halides as well, and black phosphorus, for example, that are all grown by CVT. So what's nice about it is that you do get these nice crystals that have, sometimes you can see the facets very nicely, millimeters big and so forth, and you can do nice measurements on these. And they tend to be pretty high quality crystals as well, compared sometimes to flux methods, for example. So let's go into a little bit about how CVT works. Here you're working in a closed system, right? You have a closed ampule. You want a tube furnace so that you can put on a well-controlled temperature gradient. And there are a couple of things here. We call this the charge zone, which is your starting materials. And you may want to think about, again, what do I put in there? Am I starting out with the compound itself, or am I starting out with the starting element, the constituent elements, right? And you have to think about where the crystals are actually going to grow. There are two separate parts, right? And so how do you think about the separate parts? It actually just goes back to Gen Chem 1 and thinking about chemical equilibrium. A plus B goes to C plus D. And every spontaneous process will be driven by a need to reach equilibrium, right? In chemical reactions, we use something very convenient called the equilibrium constant, capital K, all right? And that's and we use something called the law of mass action, which is the partial pressures of my products over the partial pressures of my reactions, okay? And that's important for CVT because it is all by the vapors. That's, right, it's not a solid state reaction at all, okay? So, if I have products over reactants written out this way, then let's take an example of two materials that people grow by CVT. Moly disulfide and zinc sulfide in this case here, right? Common CVT reagent is going to be a halogen. So you can do bromine gas or iodine gas. Bromine is hard to work with. How many of you have worked with bromine before? Okay, what is it at room temperature? A gassy liquid, right? You open that thing and it's just fuming like crazy. And pipetting it is really tough. So what you can also work with, which I haven't put in here, is you can work with metal bromides that will decompose in your tube to release bromine. Same with chlorides. You can use metal chlorides. I think you use niobium chloride to grow niobium diselenide crystals. In that case, you're not introducing an extra metal, for example, in that case. But you can use aluminum chloride, for example. There's also mercury chloride, but I try to avoid using really toxic, poisonous things like that in the lab because it's kind of scary, right? So in any case, you can see that the equilibrium is always going to be the partial pressures of just the gas species. Solids don't enter into the equilibrium reaction at all, okay? So you can then, and the number of moles is your exponent. So you can calculate that, and remember what gets transported is not your compound does not get transported, okay? Sometimes there's this misunderstanding that the compound is evaporating and transporting to the colder part of the tube. No, in chemical vapor transport, it is the chemical species that arise from a reaction. Okay, that's what's getting transported. So the halogens tend to be gaseous species, okay, at those temperatures, so that's why we like to use halogens many times. Okay, if you recall back from undergrad days, Le Chatelier's principle is, you know, every reaction has an equal opposite reaction, sort of, right, in chemistry language. When a system is in equilibrium and is suggested to an external stressor, it wants to go back to equilibrium, and it does that by either favoring the products or favoring the reactant. And that's kind of what CVT is. You're trying to get to equilibrium, and at one end of the tube, you're favoring the product, and the other end of the tube, you're favoring the reactant, okay? So you just want to get to equilibrium as much as you can. So if the stressor is, I've increased the pressure of species A, then the reaction's going to move to decrease A. If I increase the temperature, this one's a little trickier, because it's now going to depend on whether your reaction is exothermic or endothermic, all right? Many times some of you think that crystals are going to grow on the colder end. That's not always true. If you have an exothermic reaction between your halogen and your starting material, your charge, then the crystals are going to grow on the hot end of the tube, okay? And it just follows from Le Chatelier's principle that if you're increasing the temperature, you're creating heat, let's say, the reaction's going to move to absorb heat and decrease the temperature, okay? So this is just a clear example for endothermic. I'm going to, if I have an equilibrium between this species and this one's orange, so you can see it here. High temperature, I'm going to favor this one. Low temperature, I'll favor this one because of the fact that this is an endothermic process. I treat heat almost like a reagent in this case, all right? Okay, so find a tube furnace, one that you've calibrated well, you've put in the thermocouples, and you have a good sense of that gradient. Don't just trust the controllers. Sometimes that comes, the commercial ones, get an independent thermocouple, controller, and measure throughout. And also remember that your furnaces always have gradients within them, and they can change by how well you're insulating your furnace as well, right? So try to have a sense of what your furnace looks like for the insulation that you're using during your growth process, okay? So you have your ampule, you have T1, T2, again, it depends, your charge zone and growth zone would depend on whether it's exothermic or endothermic in there, all right? This is, again, expression that you learned for Gibbs free energy is delta H minus T delta S. And again, if we want to get to an equilibrium process, we want our equilibrium constant to be equal to 1, okay? Yeah, so we want to get to equilibrium as much as possible. Once you do that and you just rewrite the term, you'll see that the optimal temperature, the growth temperature of your crystals, is going to be the enthalpy of the system over the entropy standard, okay? So if you can look those up for your material, you can find what temperature you should be operating at. And many times we don't know, right? We just guess. You see in the literature 500, 400, something like that. Try to actually look up the thermodynamic tables, CRC handbook, or I don't know, NIST has them probably, and see if you can get to that optimal temperature, okay? Once you have that optimal temperature, now apply a gradient. Now you apply the gradient. Typically 50 to 100 degrees Celsius is your gradient that you want, okay? I know some of you, I talked to you in the poster session, you mentioned like higher than 100. I think that's okay. If you're like at 140, 150, that's probably fine. If you start getting to 200, temperature gradient, you may not get, you may not be transporting your agent correctly, or the molecule that goes in there, okay? So, also another thing about crystal growth is many times we want it to be slow, right? Because we want to minimize nucleation of many crystals, because then in the end you'll have a nice, beautiful polycrystalline mass at the end of your tube. And you want to avoid that. You want to have as large crystals as possible. You want the pressure at temperature to be about 1 bar. 1 bar. This is a mass transport type of technique, so if the pressure is too high, you will be diffusion limited again, and so the transport agent will not move sufficiently to grow nice single crystals, okay? And, you know, I said about 50 to 100 degrees, your ampule diameter should be 10 to 20 millimeters, and, you know, don't make it too long of a tube, obviously, because then it'll introduce too many gradients, temperature gradients in there. It'll be hard to control. So 100 millimeters to 200 millimeters in length is typically what you want, okay? So this seems to work really well for many systems. Okay, and these are just examples of things that we've grown. This is, you know, a potential alter magnet when you have it at 1/4, and it's the same, grew these here. I had my student, or my postdoc rather, Ryan, grow these copper chromium thiophosphates, iron, nickel thiophosphates, selenophosphates. It's a really versatile technique. You can make many crystals this way. Okay. I will answer all questions on CVT after this. I'm going to move on to hydrothermal. So some of the largest crystals that are known are grown by actually sort of these quasi-hydrothermal conditions, that is, using water now to help transport your material, okay? So many minerals, for example, like quartz crystals, the largest ones that were grown in the lab were done by Bell Labs in the day. They were very useful. Then you didn't have to go to nature to grab these high-quality crystals from Brazil anymore. You could just grow them. And it's actually one of the techniques that's well used for growing minerals today. It's very old. It's, you know, mid-19th century. And there are other things that you can grow that I would say, you know, we talk about silica, but there are many kinds of silicates, open ones called zeolites that are frameworks. And there are also new frameworks. The Nobel Prizes last year in chemistry was for MOFs, metal organic frameworks, which are made through these methods, hydrothermal, solvent-thermal methods. This is an example of a MOF, for example. So it allows you to access, again, those metastable parts that conventional solid-state chemistry would not give you access to. So that's the nice thing about it. What it is that we all know that water is, sometimes we call it the universal solvent. It's a polar solvent. And what happens is, as you put it under pressure in these autoclaves, you actually change the dielectric properties of water, okay? So you can see the viscosity changes, the dielectric constant changes, and the density changes. So things that wouldn't have dissolved in water before, like if you put silica in water, it's not going to dissolve. If you now go to those temperatures, it will, with the aid of what's called a mineralizer. So sometimes you put a little bit of acid or basic solution in there. Sometimes you can use seed crystals. It's not necessary, but if you want to grow really large ones, you can put seed crystals into them. And then these autoclaves, they basically just hold the pressure. Now, it's not a high pressure technique in the sense that you're not compressing water, right? It's just that you're able to go much above the boiling point of water when you have this vessel here, okay? So typically we go up to 220 degrees Celsius. That's the limit of this technique, only because most of the commercial ones you get as a Teflon liner, and the Teflon decomposes. But you could use glasses, for example. One of the things the most important things to know about this technique is how much you fill in and what pressure you can get to before the whole thing ruptures. Most of them are built these days to be very safe, so that there's a rupture disk, so it's not like the whole autoclave will explode in your lab, although I've heard of somebody accidentally doing that. But in this case, you know, this is a very important one. Yesterday there was a question about phase diagrams. There's For binary phase diagrams, of course, a lot of that data is experimental, but there's also something called the Gibbs phase rule, which allows you to draw many of those boundaries in the phase diagram. So you can, once you have enough data points, you can draw those in. It just tells you about the degrees of freedom that you have on, for example, here on this PT diagram, depending on how many components and how many phases are there. So phase diagrams also can be built through models, just so you know. And this was an important one for hydrothermal. Typically, this is what they look like. Again, I told you they have these ruptured discs in case they go on you. But they're pretty easy. Another thing is that it's pretty cheap. You just need an oven. You don't even need a high temperature furnace. You need an oven and you need these autoclaves, and then you can get going on these. Okay, so if you want to even go faster, there are microwave versions of them now where you can do a all Teflon autoclave and put it in a microwave, and you can do really fast synthesis. This is not recommended if you want to grow large single crystals. This is if you want to make like nanoparticles, very small particulate kind of inorganic materials. That works really well. People who work on vaccines these days, for example, they use microwave a lot, and so on. So let's get to the superconductors. The iron arsenides, we have many speakers here who have experience in that, are very interesting because you could make a whole family of different iron arsenide compounds. And then likewise, the iron selenides have very similar structural motifs. They have all these layers, consist of these layers of iron with selenium, or mostly it's been selenite, but they're also the tellurides, of course. And there was a very cool one that Jeff Lynn got me involved in, making this lithium hydroxide iron selenide. And basically the limit here is about 43 Kelvin in the critical temperature in these, no matter what you're stuffing in there, whether it's potassium cations, lithium hydroxide. Sometimes you can put organic structures in there. These are very easy to work with if you're doing hydrothermal, solvothermal synthesis. And in fact, this is the only way you can make that superconductor, that lithium hydroxide one. It's only available through hydrothermal. So unintercalated iron selenide is pretty remarkable in itself. It's superconducting at 8 Kelvin. And then if you intercalate it, you can get up to 43 Kelvin. And then there was this report that you could, get a monolayer on strontium titanate and you could get up to 65 Kelvin. There was one that was 100 Kelvin. So, we'll see how true that is. And so I've been very interested. Still to this day, I'm interested in seeing, is there something that we could do with iron selenide by putting it proximate to another material, maybe to strain the lattice or something like that. So we've worked on that area a bit. We've done, so conventional solid-state chemistry is a little bit of a black box, right? You grind everything, you put it in your furnace, you walk away for days to maybe a week or maybe longer. You don't know what's going on. With hydrothermal, same, but what we've done now at the beamline, this is the X-ray facility at the APS, you can actually follow solid-state reactions and hydrothermal reactions. So you can know something about kinetics, and in fact, we've done that with lithium hydroxide. We've done both hydrothermal and solvothermal. You can just pressurize a tube with helium. You can get up to about 7 atmospheres. And that's really the highest pressure you get to, really, in hydrothermal, is you're working 10 bars, maybe 20 bars of pressure. And you're not going too high in temperature, okay? You don't make these things at really high. 120 degrees Celsius is enough. All right, and then we collect diffraction patterns. This is just iron metal, and then we collect thousands of powder patterns. These, each powder pattern at a synchrotron X-ray source is like a second. Okay, so you're getting thousands of these, and so the only bad thing is you leave with gigabytes of data, and now your students have to work it up, and they've been really good about that. So. Then they get this lithium hydroxide iron sulfide. This is sulfide because sulfide is a little bit easier to, well, I'm going to be honest, it's cheaper to work with than selenium. So that's why we did it with sulfur, but it works the same with selenium. And you can see that if you do Rietveld analysis of all those thousands of powder patterns, you can pull out the phase fractions. And one interesting thing about this is There's a little bit of iron that substitutes. It dopes, right? We have iron 2+, it dopes on lithium 1+, and it creates a cationic layer that charge dopes into iron selenide. Presumably that's why you raise the TC to 43 Kelvin. But what we see when we do the synchrotron, for example, is that the amount of iron that goes in there is pretty dynamic. It actually decreases and then it goes away. So sometimes when we do syntheses, we get results that are not reproducible, correct? And I think one of the things that can happen during an actual reaction is, depending on when you remove it from the furnace or from the oven, let's say for hydrothermal, you may get a different composition than you think you started out with. Many times we write out in a publication nominal composition, right? That's what we think we put in there. But what you actually get out is much trickier to really know, and you have to do both the diffraction analysis and some other kind of compositional analysis in order to verify. And so we see that when we did these in situ hydrothermal reactions, that it's not always going to be the same, and it depends on when time you would end this reaction. If you get rid of all the iron in here, you're not going to have a superconductor anymore. You would probably have a boring polyparamagnet or something like that. So JP and I worked on several of these over the years, and we made a very interesting one too. I told you hydrothermal is a way to make minerals, and in fact, we made an artificial mineral that includes an iron-based superconductor embedded within it. It's called this mineral tashilanite, and what we were doing in there is putting a metal hydroxide, like lithium hydroxide, into iron selenide and iron sulfide. And unfortunately, we haven't quite gotten to a superconductor in this one because it overdopes. This hydroxide layer puts too much charge in here. But what's enticing about this is that you could put magnetic cations in here and eventually make a magnetic layer that's proximate to a superconducting layer. So that's something we're still working on. And again, it's done hydrothermally. We're able to make it, we can make it deuterated, important for those of you who do neutron scattering. If you want to find that, you do neutron scattering. So in any case, we've been able to, at least from electron diffraction, solve the structure of this compound, and you can actually make a hydroxide intercalated between iron selenide. Now our work is to tune it in a way that see we can make this superconducting. So right now we're not quite there yet. These are called layer double hydroxides, but we're working on it. I'm going to get to the fourth part, because I think there's some interesting things here, and I want to end on where do we go from here? Like, what type of superconductors should we be looking for next? Is it that easy to just, make a prediction and go after it? There are many ways to manipulate structures. One is called intercalation and deintercalation chemistry. In fact, you use that, right, whenever you're powering your lithium-ion batteries, you're intercalating and deintercalating lithium into cobalt oxide layers. But what's cool is that your cobalt oxide layer stays intact, okay? And that's what we were really doing with the iron selenides and sulfides, is keeping those layers intact and just swapping things in and out. And for iron-based superconductors and also transition metal dicocolgenides, you can insert many different species in here. So for example, you can insert lithium in liquid ammonia and then boost it by 35 Kelvin. For tantalum disulfide, you can put in these organic molecules in there. This is kind of older work. And then you can get nice superconductors, and you can move in and out whatever you put in between these layers. Some of you maybe have done this reaction. It's really a neat one. You take ammonia and you liquefy it, and the blue color is actually from a solvated electron. As you put lithium or sodium or any alkali metal, you solvate the electron, which immediately reduces the iron selenide, turns it anionic, and then it intercalates a cation inside. So it's actually pretty interesting chemistry in itself. JP and I worked on this some time ago, where we deintercalated a material. So if you make potassium iron selenide or potassium iron sulfide, you can grow really large crystals of that. It congruently melts. Ryan said yesterday that a material that congruently melts means that you have this specific composition and you can reach the liquidus line, right? And then you just slow cool, and as you slow cool, you can grow as large a crystal as possible, like Bridgman technique, you can use it. Iron telluride, iron selenite telluride, it all grows that way. Same for this compound, but you're left with that potassium. So what we've done is we grew large crystals, and then we removed the potassium, and we made pure iron sulfide crystals this way, and made a superconductor. It's not as high as iron selenite, but we thought it was really neat that we could make an iron sulfide superconductor. If you look at a phase diagram of iron and sulfur, you're not going to find that compound on that phase diagram. Okay? Again, the energy landscape is much more complex than we think. There are metastable forms of iron sulfide that you're not going to find here because these are our thermodynamic products here. So iron sulfide has a whole lot of different compounds and structures, and you're always fighting against that to make something that just looks like these layered ones here. And so through these soft chemistry ways, you can actually access those and make, for example, new superconductors. This was just demonstrating how we do this. This is one of my favorite examples, and I'm actually coming back to it. I feel like it's been neglected for too long. And it's just the add water, the instant superconductor that Jeff Lynn worked on here. And this is a sodium cobaltate, as I just told you, your lithium-ion rechargeable battery. When John Goodenough made that, it was cobalt oxide. Today it has nickel and other stuff, but you can also just put sodium in there, deintercalate so much sodium, and then it becomes a superconductor. People didn't know in the beginning why that was. It turns out that if you just leave it out in air, it soaks up moisture, and then it becomes superconducting. So this is from Bob Kava's group, and Ray Shack was a postdoc with him at the time. And they actually found this sodium cobaltate superconductor. And then Jeff and Ching Wang and Bob Kava solved the crystal structure and found out that indeed water just comes in and expands those layers from each other. And so we've revisited this, and actually you'll see that in the practical. My student Coco will take you through. She's made the compound. You start out, again, just a conventional solid state technique. Sodium, I think she used sodium carbonate or some kind of hydroxide, I don't remember which one, with cobalt oxide. And then you just fire it up, you make your compound. Then you add the bromine. I forgot to add here, you put it in acetonitrile solvent so that it's not too difficult of a reaction. And you remove sodium because the bromine is going to reduce and oxidize the cobalt. And the sodium just pops out when you do that, okay? And so you go from 0.77 to 0.33, and then you add D2O. You can do it in a controlled manner, and the water molecules just come in, coordinate around the sodium, and it really expands the layers together. And so not a superconductor, superconducting. These are some of our preliminary susceptibility. And I told Coco, can you reproduce this for potassium? And she did. Actually, we found a new potassium intercalated material with water. So it's really interesting chemistry for me, and I think also it's interesting to see what other new superconductors we can come up with. In the interest of time, I think I'm going to go to the very end, JP, so that I can get questions. What do you think? What time did I start at? 11?
Yeah, we should leave,
At 12?
Yeah, another minute or so, it's okay?
Yeah. Another minute, okay. Well, right. All right. There are other kinds of techniques. One of the ones that I wanted to leave off on is this soft chemical technique where you react, say, a metal oxide like a perovskite or perovskite-related material with hydride. And you can make, as was discovered by Harold Wang and others, that you can make now, for example, nickel oxide that was a perovskite into an infinite layer, so it looks more like a cuprate now, right? It's 4-coordinate square planar geometry, and this was discovered to be a superconductor in 2019. You can see here the resistance curves. Only if you have the right doping level, right, where you're mixing in the rare earth and the alkaline earth together at the right ratio, and then doing that hydride reduction. The H- just removes that oxygen. So again, it's another soft chemistry technique, very effective for making new compounds, and in this case, making a new exciting analog to the cuprates from the nickel side of things. Where do we go from here? There was this article that came out on like what's the path forward, right, to the room temperature superconductor. And I thought it was interesting. You know, this is, I think, Rio, you showed a similar plot earlier today. And but there are some things in here that you should be careful with. Of course, you can go high, but you know, now that necessitates pressure. And then you got to be careful when you read this literature, because nowadays, right, some of these are problematic, I would say, and now retracted some of these. And then for this one, for example, iron selenide at 100K it's not really been reproduced with resistivity measurements on a single crystal or any other kind of bulk material. So be careful when you see sometimes this, the literature and looking at these plots. But I think it's still exciting to think about, for example, hydrogen and hydrides, whether those can be superconducting. And I still think it's interesting to look at the iron selenide materials and see if there are other ways to boost that TC. So I'll leave it at that. I don't know if y'all seen Avatar, but remember that unobtainium was the superconductor. And and I think that's why you have these floating islands. And it's the room temperature superconductor. It must be. Otherwise, you know, how do you get that? So how do we get unobtainium? I don't know. But I think there are now these really interesting suggestions. One from our very own colleague, Ichiro Takeuchi, and JP and I went on that paper too, where training models on known databases, this one's from the NIMS database in Japan, and predicting potential new superconductors. And so now there are many papers that have followed up on this, making their own predictions. But I think it could be very useful, but I would say make sure to include the chemist in your deliberations when you look at these lists, because some of them are like, yeah, that could potentially be doped, and some of them are like, no, you can't dope a silicate or a germanate or a phosphate and make it conducting, not even a metal, much less a superconductor. But there are some other ones that definitely might be able to get there, right? And so I think a combination of looking at it this way with some physics, some grounded physics and chemical intuition potentially could get us to maybe not the room temperature superconductor, but you know, something that's higher TC. So anyway, that's my talk, and I'm happy to take any questions.
So who knows why the mountains are floating?
You just said it's superconductivity.
Yeah, but why?
Why do they float?
Pandora's magnetic field.
I think it's the Meissner.
Yeah. Wow. Thank you, Professor Mike.
Okay, yes, question.
Just James Cameron is off his rocker.
There was a question here.
Yeah, go ahead first.
Yeah.
So you were showing that CVT growing methods can grow like higher quality samples. Is there cases where CVT like grows more dirty samples in comparison to flex?
That's a great question. I think that with CVT, what you may run into is potentially defects on the surface, like maybe anion vacancies and things like that, because you don't have that nice enveloping flux around it. So one thing that you may want to think about if that is the case is to anneal your crystal in, say, selenium or sulfur, so that you can regain that surface, if that is what you're worried about. Nick, you had your hand up because you have an example, I'm guessing. Moly ditellurite.
Iron arsenic.
FES, the hexagonal?
FEAS grows better crystals with the flux.
Yeah. Yeah.
Yeah, probably. I don't know. But
Yeah, I would think so. Like perhaps the equilibrium is favoring a vacancy phase that decomposes during that temperature. Yeah, so that could be it. So I wouldn't say blanket, CVT is always better than flux, but many times it can be, yeah.
Thank you.
Yeah.
Hi, awesome talk.
Thank you.
Good to meet fellow chemists. I have actually a couple of questions.
Sure.
So when you were talking about making the, I think the lanthanum-based superconductor at the very beginning, you said you needed excess oxygen to make it. What happens if you don't have excess oxygen? Because the structure without the excess oxygen is not charge balanced.
Oh, you just get copper 1.
Oh.
Yeah, it's all copper 1, and all your coppers previously in square planar geometry and now in linear geometry. Like copper 1, silver 1, gold 1, they like linear coordination. So it does. That's what you end up with, a 1, 2, 3, 5.
So when the oxygen is being lost, it's the copper that's getting...
The copper gets reduced. Yes. Yep.
Yeah. My second question was, during the hydroflux part, you showed this picture of these 3 necked round flasks with the blue
Oh, yeah.
stuff.
Mm-hmm.
And you said it's from solvating an electron.
Right.
How do you solvate an electron?
So the electron is on the ammonia molecule. So that's the cool thing. If you put sodium in water, what's going to happen? Some of you have done that, I'm sure, right? It's pretty fun to see. My chemistry teacher did it in high school all the time. And you see it, right? It's sodium, all the alkali metals will react immediately with water. Okay, but ammonia is a very interesting solvent. It actually does not decompose upon getting that. It just accepts that electron, and that's what you're seeing is the ammonia with that extra electron on there. All right, and then what's nice about that reaction is as soon as you put in the compound that's going to be reduced, you see the color change from blue to colorless because the reduction happens so fast. The organic chemists call this a Birch reduction. They use it, I think, for, I don't know what to synthesize, but yeah. So it's just a trick that we took from them, and we use it. And if you keep putting more alkali metal in there, it actually starts to turn into like a golden color, like a liquid gold in there. Yeah.
Oh, yeah.
Yeah, it is really cool.
It was here, and then you have a question?
Yeah. So I have a question on the hydrothermal one. So more is on the solvent thermal. So I was wondering for the temperature in the solvent, because when we do solid state synthesis, we can look at binary phase diagram.
Yes.
But there's not such a thing for hydrothermal. So how do you determine what temperature you can go up to, and how does that affecting the results you're getting?
Yeah. So it's a little bit of a complex answer. It depends on what temperature your reagents will dissolve. So with hydrothermal and solvothermal, it's like a flux synthesis. You want everything to go into the solution so you can saturate it with that species, and then you want it to slowly precipitate out on a few nucleation sites so you can get crystals. Many times you won't get crystals, you'll get a polycrystalline sample in that case, unless you had a seed in there for some reason, right? But the temperature is really determined by how much you want to dissolve your reagent. In our case, for the iron-based superconductors, we wanted a low temperature because we wanted to slowly dissolve iron metal in there. If you dissolve it too fast, or say I started with iron 2 chloride, let's say, something like that, I make a whole bunch of iron oxides, which are ferromagnetic impurities, right? And then you don't get to see your superconducting phase. And so it depends on the species that you're starting with and how fast you want to dissolve it, I would say. You definitely have an upper limit, as I said, 220 degrees Celsius, because your Teflon decomposes. But the other temperatures you have to sort of play around with to know how they go into solution.
So I wonder for the solvent, like how would you choose the solvent? Like, did you think about like a polar?
Yeah, that's a good question. It depends. So most of the time you want a polar solvent. So you could do water, you could do DMSO, you could do DMF, right? And those just have different boiling points. So you want to play around with that. And because of that, they have viscosity. One thing I didn't say about hydrothermal is that it's just like CVT, it's mass transport as well. So you don't want a super viscous solvent. You want something that will allow the mass to move, the species to move through there. If you can do it, it's very hard to do these days. I don't see many people do it. If you can apply a temperature gradient on your autoclave, you have a better chance of growing high quality crystals, or bigger crystals that way. But it's hard to do.
Yes.
Thank you for the great talk. I have a couple of questions actually. My first question is about what the research process looks like, decide what a doping will be or the amount of it. It's just like trilinear, and this is a question for mostly how much of a baseline, I think.
Like how much? Yeah, that's a very good question, and I don't know if I'm gonna sound like like an alchemist in my response, but when I told one of my students, Chris, I don't know if Chris is here, we made these cocalgenides that are mod insulators. And I was like, mod insulator, dope that thing, see what happens, right? And so we did the liquid ammonia experiment, and I said, let's do 15%, because I always, with electron doping, I guess whole doping is, well, 15%, you get like this nice optimal TC in many cases. So it's just intuition by looking at what's happened before when it comes to electron or hole doping levels as to what we'll get. Unfortunately, that's, we haven't gotten a superconductor yet, but that's one of the things that I start thinking about is like, what do the phase diagrams look like for the superconducting domes of other known systems, other mod insulators, for example, and then we target there and then start moving maybe 5% away from that and to map it out. Yeah.
Thank you so much, that makes sense. That's a difficult task. You definitely need some intuition to work with. My second question is just about how you integrate organic materials into your layer, because I imagine the methods can be incompatible with pipes, like really high.
Right. So it turns out, like for example, if you do solvothermal, some of them will insert themselves in there. I didn't mention the ones that we tried. They're usually amines, so ethyleneamine, and we did diaminopropane, cyclopropane, and cyclohexane, sorry, and some others. And what happens if you're working with cocalgenides is that amines go in really fast, like even ammonia. And there's just something about amines matching really well to bond, like hydrogen bonding to sulfide, tellurides, and selenides that makes it easy for organic structures or organic compounds to go in. We tried other things, and a lot of it is, unfortunately, Edisonian in approach. We tried, for example, alcohols, glycols, and some others, and they just don't go in. But yeah.
Thank you.
Okay, we better get to lunch soon, so let's thank the Frankie. Okay, as they say in Italian, lunch time. We're back at 1 o'clock.
Is that Frank in there?